All right, yeah, so today we're going to talk about the case for distributed shared memory databases with RDMA-enabled memory disaggregation, right? So this paper kind of tries to bring back the idea of shared memory databases from like decades ago and say that, hey, because now we have RDMA technology, we can, look into the remote machine's memory decently, fast with high bandwidth. Maybe we can start building like pools of memory, disaggregated memory, and use these pools of memory as like shared memory for the databases, right? So the idea kind of goes from like, the way the cloud has been progressing in a way, right? So, we like to think about servers as like this kind of complete box that has some CPU, memory, storage and whatnot, right? And that's how it used to be. But now in the cloud, this box is a little bit more complicated, right? We already have kind of disaggregated, storage that is shipped to like a shared storage infrastructure between tenants and whatnot. So, the VM that you actually get is going to have CPU, memory, maybe access to local disk, which is not a lot, but most of the stuff, like most of the storage is already kind of shared and disaggregated, right? So it sits somewhere else. And that works perfectly fine. And what this paper says, well, we can do the same with memory, right? Like we can create pools of memory that are kind of in a separate memory, only machines that have like very limited CPU and whatnot. And we can use this memory. We can like bring this memory into our like powerful compute machines that have lots of cores, but may not have like a lot of memory. Well, they specifically say that this, may be a good idea for kind of data-driven applications that rely on like using a lot of memory, right? I think one of the key motivations, for the paper, like when they talk about RDMA, is they say, hey, this is how quick, RDMA can be, right? Like the access to the memory over RDMA. 0.8 microseconds latency and decently high throughput, like 200 gigabits per second. So this is still slower than obviously using the main memory. And like latency wise, it's like up to 10 times slower. But they say it can be good enough. Now there are a couple of caveats to pay attention to when we talk about this, like capacity, the speed of RDMA, and that's because RDMA has like it's a very tricky, set of APIs, right? So on one hand, we have one-sided RDMA, which is the fast one, like the really fast one, right? And it's one-sided because it doesn't involve the remote CPU, right? So you can just access the memory through the network card on the host machine, and no CPU on the host machine, remote CPU is involved, right? So, but it has limited capabilities, right? You can read and write, you can write something, but you don't really know if, it was written successfully. It's kind of, one-sided, fire and forget, and you hope it works. So, if you want to build something reliable, maybe like if you use one-sided RDMA, maybe, after you write something, you need to go and read to make sure that it's actually there, which, obviously wastes both bandwidth and, creates like multiple round trips, for just one, let's say, memory write operation. So on the other hand, we have two-sided RDMA, which, provides you the acknowledgements, right? So it's more of like a send and receive type of API. But it actually uses the CPU on the remote machines, so it's potentially not as fast. And obviously now we need to have like more CPU on those like memory machines to be able to use this two-sided RDMA well. And we covered some RDMA stuff in like previous papers in this group. I just give some paper numbers. I think paper number 43 talks about like consensus over RDMA, 67 is on storage, and yeah. So that's kind of the background, right? So and the rest of the paper is like laid out around this idea of building the database, which has the compute node, on like multiple compute nodes, some memory, local memory, and all of this other stuff, all of the other memory is this distributed shared memory, DSM. And you access it through this RDMA links and whatnot. So kind of very basic idea, just use that pool of memory, and everyone has access to all of that same memory. So what can go wrong?
Lots.
So in the paper, they really talk about things that can go wrong, or things that are unsolved if we try to build this type of database design, like database architecture. And they start with the challenges around this distributed shared memory. And they say that well, we need to expose some kind of abstract APIs for the data stores, databases to be able to use that memory, kind of like local memory. Right, so we need to have memory allocation APIs, and obviously it needs to deal with like virtual memory addresses specified by things like maybe node ID in that memory pool and some offset and whatnot. They also talk about data transmission APIs, mostly for well, you can allocate the memory, you can use the memory, but if you actually want to use the memory on the compute, you need to transfer it. Right, to the local CPU. So transmission APIs, or if you want to cache it locally, that's also important. And they also talk about function offloading APIs. I'm not sure how well it fits in kind of the rest of the big idea that they have here. But the function offloading is like, hey, maybe we can actually put some stuff, like compute some stuff on the memory side of things, right? So on the memory like machines, which by the way have limited CPUs. So I'm not sure how well and predictable that will be, but anyway, that's
muddies the abstraction. It certainly muddies the abstraction.
Mm-hmm. But that's their wish list for the APIs to to build those types of databases, which by the way don't even have like a concrete design of a database or concrete architecture. They just say we want to use those memory pools somehow, right? So the other challenge is the durability and availability of those shared memory pools, right? So
no shit.
Yeah, if a memory node fails, well, what can we do, right? And one of their proposed solutions is as silly as backup to storage, which kind of defeats the purpose of having fast memory and whatnot if you write everything to disaggregated storage first. If not that, then we need to replicate the memory nodes, right? Have like multiple redundant copies of all of that memory. And then they also worry about the cost of memory. So maybe we could use erasure codes and things like that. And
that's crazy shit.
And a lot of the stuff that they talk about in that section are a bit contradicting. So they when they talk about durability, they say, hey, let's preserve the logs, kind of have a redundant logs in memory, write ahead logs and whatnot. And then they talk about availability, and all of a sudden, now they start to worry about the memory consumption, which, by the way, didn't really bother them when they talked about having redundant logs, and said that actual state, maybe it should be erasure coded. So there is a bit of contradiction here and there, but yeah. A big set of challenges that they talk about are related to concurrency issues. And actually, they have an entire section in the paper on concurrency control challenges, but the concurrency issue shows up in other challenges that they use as well. So despite saying that, hey, this distributed memory, shared memory, the DSM is fast, they still say, well, local memory is faster, like an order of magnitude faster, right? So it would be nice to use it for caching, but if you use it for caching, you can open a lot of other problems, like cache coherence, right? So if we have like all of these hundreds, if not thousands of different compute servers all interacting with the same memory pool and all have their caches, well, how do you make sure that no two machines work off different version of data that they cached, right? So there is no like cache coherence protocol that is implemented in any kind of hardware for these types of systems, so it needs to be done in software if we go this route. So one solution that they say is, okay, well, don't use the cache, don't use the local memory, just go for no cache, no sharding, just always work with the remote memory. The second solution that they say, well, we need to build the cache coherence solution of some sort, and they kind of hint at some issues of how do you like manage that and whatnot. The third solution, hey, let's build a shared memory database, but let's shard it. So the compute workers are sharded or kind of virtually sharded. So each compute node is only responsible for like subset of the address space, and no other compute node can touch that address space. So like if you're the exclusive owner of a particular address space, then you can cache it locally without worrying about the cache coherence and whatnot. But then, we're kind of coming back to, our more traditional designs, like database architectures right now that are sharded, albeit they don't have like distributed shared memory, but yeah, like what does it actually give you? They also, talk about some of the transactional stuff. So they say, okay, if we don't do sharding, right, if everyone can access all of that shared memory, then we don't need, distributed commit protocol, like no need for 2PC and such. Well, I mean, it doesn't really
doesn't
solve
mean
a lot.
anything unless they talk about what's durable and how's durability doing.
Yeah. So the durability of this distributed shared memory, they don't discuss it. They don't discuss how to build those things
Right.
whatsoever.
2PC is ridiculous to discuss.
So, but talking about like transactional stuff, no need in 2PC. Okay, great. But you still need to have to provide transactional isolation, and now with like potentially hundreds, thousands, or even more cores, all like accessing the same shared memory. So they talk about kind of traditional solutions, two-phase locking, optimistic concurrency control, and try to talk about like why some of the things may not work well with RDMA, right? So and how maybe we can try to work around it, but they don't spend more than like a paragraph each. So again, it's just mostly a list of problems, right? So if we go in this route, we need to have some kind of concurrency control protocol to provide isolation for our transactions, such that it works on these thousands and thousands of cores over RDMA. Yeah, they also talk about kind of more caching problems. They refer to them as buffer management, but that's mostly like how to move the data between local memory and distributed shared memory, right? And your like cache algorithms may need to change some of the priority because they say that local memory is faster, like 10 times faster, but it's not the same kind of speed up you get from like more traditional caching systems, right? Where you go like main memory versus storage, right? It makes sense to keep stuff in main memory versus storage because main memory is like multiple orders of magnitude faster than durable storage. So they say that we need new algorithms to manage those types of to manage cache that actually focuses not so much on cache hit rate, but on the overall runtime of the software. So you should not spend too much time trying to improve the hit rate if that's like very expensive, right? So because the difference is like only 1 order of magnitude versus like 2 or 3. So Yeah, and kind
I
of
think the thing that bothered me in this was they just didn't have any notion of the role of this memory. How did it fit into the overarching transactional system? What is it doing for you? They just said, yeah, we could have this fast thing, and it's pretty cool.
No. They treat this like I think what they want to do is they want to treat this as kind of one, multi-core database with like all the memory. So just try to take, your, single server, Oracle database and whatnot, and blow it up by the virtue of having the distributed shared memory that is like very large, and you can scale this memory more if you need to, like separate from compute and whatnot. But the problems kind of remain the same. Hey, how do you provide, if you have this memory, you need to provide isolation, and they don't go like beyond thinking about
didn't even look at Oracle Rack or at VAX clusters or at IBM Power, what's it called, data sharing, DB2 data sharing. They didn't look at that stuff, which has solved these comparable things.
So, and yeah, the final thing that they talk about is like index, right? So how do you design the indexing strategies? They tend to be designed for a particular architecture and hardware, right? So magnetic disks, then we had SSDs and whatnot. So now it's going to be like DSM over RDMA. So they say something new needs to happen here. And another problem is like what happens when, again, like all of these compute workers access that index at the same time, right? So it needs to be like highly concurrent. So that's more or less it for the paper. It just creates, like, gives you the list of challenges, and it does have some pointers to the prior research from like decades ago, but most of them just say, hey, that's like their comment, at least, that's so old it's not applicable, we need something new.